In this Statistics with Microsoft Excel video, we're going to look at a hypothesis test, comparing the association between two categorical variables. Under the null hypothesis, those two categorical variables are not associated with each other. In our example, we're going to have two binary categorical variables. We'll calculate an x-squared statistic, a critical value for the chi-square distribution, and also a p-value for our findings. So we've calculated the measures of association. We looked at the confidence intervals, and we saw that, at least for our example here, never did we have that the value of that measure of association under the null hypothesis is within our intervals for our confidence interval, thereby rejecting a null hypothesis, accepting the alternative hypothesis, in this instance that these two variables are associated with each other. So I want to create a brand new sheet. What I'm going to do is go back to my original data set. I'm going to click in any one of the cells, hit Control or Command A, then Control or Command C to copy all of that. I see my marching ants. I'm going to create a brand new cell. I'm going to create a brand new sheet, and I'm going to say paste values. And I might also want to insert and create a table. My table does have headers. I'll select that and hit OK. Let's go down and rename the sheet. This sheet I'm going to call Pearson. What I do want to conduct is hypothesis testing, and this is a Pearson's chi-square test. A chi-square test for independence or chi-square test for association. All names for the same test. I want to know if there's an association between these two variables. Now, when we did our measures of association, we saw that for none of the three measures did the value under the null hypothesis fall within our confidence intervals, showing us that we could reject our null hypothesis and accept the alternative hypothesis. The null hypothesis being that these two variables are not dependent on each other, they are independent. The alternative hypothesis that they are associated or they are dependent on each other. The value that someone gets for the exposure variable will determine what value they get for the disease variable. Now for this, we need a contingency table or table of observed data. This is categorical data, and all we can do is calculate frequencies. So I'm going to click in one of the cells in the table. I'm going to go to Insert. I'm going to hit Pivot Table. The table will already have been selected for me. I just have to say where I want to put the pivot table. Let's put that in the existing sheet. I'm going to click my selection button. Let's go back up to cell E1. Expand again and hit OK. Now, as in the previous lecture, I see exposure and disease. I want to drag exposure down to the rows area, and I want to drag disease down to columns, and any one of the two I can drag down into values. Let's just click, hold, and drag. And I see my contingency table. Please look at the previous video where we talked about this contingency table. Now here are three values that I need to decide on or calculate. The first one is my alpha value. Let's set that to 0.05. The degrees of freedom for this Pearson chi-square test is going to be the number of rows minus 1 times the number of columns minus 1. And by that we mean the number of levels for each of these two variables. And in both cases they're binary. So 2 minus 1 is 1, and 1 times 1 is 1. So we're going to say equal. I'm just going to say, do it longhand, 2 minus 1 times 2 minus 1. And remember that 2 comes from the fact that these are both binary variables. They've got 2 levels each. And that leaves us with a single degree of freedom. Let's calculate the critical value for the chi-square distribution under 1 degree of freedom. That's going to equal chi-sq. So I'm looking for chi-sq.inv. My probability, remember, is 1 minus my alpha value, comma, then the degrees of freedom, which is 1, and we see a critical value of 3.841. Any x-squared statistic larger than 3.841 will be in the zone of rejection, and we reject the null hypothesis. If it is smaller than that, we fail to reject the null hypothesis. Now that we have our table of observed data, we have to calculate a table of expected values. Now to calculate the expected values for these 4 joint frequencies, we're going to go cell by cell, and we're going to look at the row total and the column total for that specific cell. So if we look at this first cell, it has a value of 751. Its row total is 8506, and its column total is 1374. So let's start there. So we're going to say equal, that's row total times column total divided by the total number of people in our study. And that's under the null hypothesis what I would have expected. Now what we do make use of here is the specific law of multiplication for probability. If those two variables are indeed independent of each other, this is what I would expect. I would expect that the probability of exposure and disease equals the probability of exposure times the probability of disease. So let's go to the second cell in this first row. That's 7755. So to calculate its expected value, I'm going to go equal its row total times its column total divided by the sum total. And I get 7802. Now let's move down to the second row, the first column. So that's going to equal that 623, its row total times its column total, divide by sum total. Great. And then for the last one equals, that's the 7479, its row total times its column total, divided by the sum total. And there I have my expected values under the null hypothesis. If you give me 16,608 people, this is what I would expect under the null hypothesis. Now we have to calculate our x-squared statistic. Now to do that, we have to consider the difference between what we observed and what we expected. So let's calculate those four values. So I'm going to start right here. You can start anywhere on the sheet, of course. I'm going to say equal, and I'm going to do two open parentheses, and I'm going to say observed. So I'm starting in that first row, first column cell, observed, minus expected. So it's corresponding expected. Close parentheses, it's that difference. To the power, so that's shift 6, and 2, close my parentheses, divided by expected. So it's observed minus expected squared divided by expected. And so that's 3.17769, etc. Let's go to the next one. Equals, open parentheses. I'm going to click on observed. That's that 7755 minus its corresponding expected. That's the 7802. Close parentheses to do that subtraction. Square that subtraction. Now I'm done with the numerator. Close parentheses divided by expected. So click on the 7802 once again. Now I'm going to go to the next row. That's going to equal, open parentheses, that is observed, 623 minus this is expected, 760, close parentheses, square that value, close parentheses for the numerator, and the denominator is just the expected value again. Let's do the final one, open, that is observed, 7479 minus expected, 7432, close parentheses, square that, close parentheses for the numerator, divide by, then the denominator is the expected again. And there I see the values. Now I can finally calculate my x-squared statistic. Let's do that. That is going to be the sum, open parentheses, of these four values that I calculated. Close my parentheses, and I see an x-squared statistic of 7.09. That is larger than my critical value. I reject my null hypothesis. My x-squared statistic among all possible x-squared statistics under the null hypothesis is much bigger than this critical value. It falls in the zone of rejection. I reject the null hypothesis that these two variables are not associated. I accept the alternative hypothesis that these two variables are associated with each other. We can of course also calculate a p-value. That is going to be the area under that probability density curve. And I want to know the value from 7.1 towards the upper tail, towards positive infinity, that area under the curve. So what I'm going to do is say equals chi, there we go, chi sq.dist. I'm going to put in my x-squared statistic from my study, that's 7.1, comma, the degrees of freedom was 1, comma, cumulative, let's select true. Now I am not done. I'm going to close the parentheses and hit enter, but I'm not done. Remember, this is going to calculate the area under the curve from 0 up till the point 7.10, and that's not what I want. I want the upper tail. So say the value 7.1 or more extreme. So I'm going to go back in there, perhaps up in my formula bar, and I'm going to say 1 minus that chi square. And that leaves me with a p-value that is definitely less than the alpha value. Of course it would be, because the x-squared statistic is beyond the critical value. And so once again, as with our decision rule, as far as the critical value is concerned, and what we saw with our three measures of association, we reject the null hypothesis. And so this is how we would do a Pearson's chi-squared test when it comes to two binary variables.